So in previous videos, we've talked quite a bit about the idea of factorial designs, where you have two or more factors, like maybe two independent variables, and thus you've got a group of participants for every combination of the levels of those factors. Like with a 2x2 factorial design, you had four groups that you would be comparing to see if those groups differ, if there are any main effects and interaction effects between those two variables. At the time, we didn't get into how you would test inferentially to see if those effects are statistically significant. So we looked previously at an example where we might test the cage conditions of lab rats to see if it affects how many mistakes they make in a maze running task. We had two factors in that example, their feeding schedule and their housing conditions, and each factor there had two levels. So we called this a 2x2 factorial design. Now I gave these numbers as some made-up data where we might see, let's say, an average of 6 maze running errors in the free access and good housing group, and 22 errors in the free access and bad housing group, and so on. It might look at a glance like feeding schedule doesn't really matter since the overall average for the whole free access row comes out to a mean of 14, and the overall average of the entire fed daily row comes out to a mean of 14 as well. Whereas with housing, it might look at a glance like good housing is better than bad housing because it led to fewer errors just on average overall, right? But what if we want to know if any of these comparisons are statistically significant? What if we want to use this data to conclude whether there is a main effect of feeding schedule or a main effect of housing based on our data, or for that matter, if there's a statistically significant interaction effect? In which case the main effects may not even be straightforward to use or interpret. So for that, we're going to need some inferential statistical tests. In essence, we're going to have to do a stats test for each hypothesis. For each possible main effect, meaning each factor on its own, we can test whether it has a statistically significant effect. But also for each possible interaction, that is, for every possible combination of factors, we need to see if that interaction is statistically significant. Which means really, for each one of these tests that we're going to do, we're going to have a null hypothesis. And for each one, we're going to do a form of basically an ANOVA test, where we'll calculate an F ratio and reject or not reject that null hypothesis. And rejecting the null would mean there is an effect, either a main effect, if that's what we're testing, or an interaction effect, so whichever one we're testing. And thankfully, in a modern statistics program, all of this gets run at the same time as part of what we just call a factorial ANOVA. So it's like a normal, simpler one-way ANOVA that we've seen in a previous video, but here for two or more factors. So just for example, if we're doing a 3x6 factorial ANOVA, we had a 3x6 design, that means we've got two factors, right? A factor with 3 levels and a different factor with 6 levels. So one factor might have a significant main effect, but maybe the other factor doesn't have a significant main effect, and then there might also be a significant interaction effect, or not, depending on the stats come out. And of course, if there is an interaction effect, then do be very careful about how you interpret the main effects, just as we do with all factorial designs that we've talked about. So imagine we're doing a 2x3 design. How many statistical tests do we do? Well, you've got factor A, the one with 2 levels. So the null hypothesis to see if there's a main effect of factor A would be H0, saying that the mean of factor A's first level is equal to the mean of factor A's second level. Or to make it easier, you could just use words. The null hypothesis of the top line there could just be that both levels are equal for factor A. Now to test the main effect of factor B, the null hypothesis is again that all the levels are equal for factor B. So you could write that mu of B level 1 is equal to mu of B level 2 is equal to mu of B level 3, or you could just use words and say they're all equal. But then we've also got a statistical test for the interaction effect of factor A by factor B. The interaction like A by B, A times B. The null hypothesis would just be that there's no interaction. So if we reject that, we have found a statistically significant interaction. But the point is, we need to do 3 statistical tests. or have our stats program do it for us, whatever. But we need to look at the results of 3 statistical tests, meaning we need to find 3 p-values, and for each one, choose whether to reject the null or not reject the null. So pop quiz then. If we had a 6 by 8 factorial design, how many statistical tests do we do? You might pause and think about or even try writing out the hypotheses before unpausing. So don't be fooled here by the numbers that we have, the large number of levels. We still just have 2 factors here. We still just have 2 independent variables, right? So it's still just 3 statistical tests. We do 1 test for each factor to see if there's a main effect of that variable itself, but then an additional statistical test for the interaction between the 2 factors. So the null hypothesis for the first factor is just that all 6 of its levels are equal. The null for the other one is that all 8 of its levels are equal. And then, as always, the null hypothesis for the interaction effect is that there is no interaction effect. Now, things get messier if we have more than 2 factors. Like imagine an A by B by C design, like a 3 by 3 by 2 design, for example. We would have to run a test and check a p-value for 3 different main effects, right? The main effect of each variable on its own. Is there a statistically significant main effect? But also the interaction effect of each combo. So like, is there an interaction of factors A and B? You test that, you get a p-value, you reject the null or fail to reject the null. And then for B and C together, check if there's an interaction. And then for A and C, check if there's an interaction between them. And for that matter, we even have to check if there's a statistically significant interaction of all 3 factors when you take them all together. Like some new layer of change that comes when you take all 3 into account at once. So that is a possible 7 effects that we'd have to do a test for. 3 main effects plus 4 interaction effects. So let's do another pop quiz and see if we've kind of got the idea of this. Let's say for a 3 by 2 by 4 design, how many statistical tests are there? Try unpausing and writing them all down before unpausing. So we would check the main effect of each factor on its own with a null hypothesis, which is basically always going to be that all levels of that factor are the same. So that's the main effects we'd test. But we'd also check each interaction effect, meaning every combination of those 3 variables. So like A and B, B and C, A and C, and even A plus B plus C, like those all 3 together. So for all of those, the null hypothesis is just there's no interaction of the relevant factors here. So if we reject the null on any of these, we've found an interaction effect. Now, just to keep all this stuff straight, when you are dealing with factorial designs, you would find the number of groups that you need for your whole design by multiplying the numbers that you see, the numbers in that design. So for example, a 3 by 2 by 4 design, that requires 24 groups. So there's 24 different combinations of those. That's 3 times 2 times 4. Now that design just has a total of 3 factors, since each of the numbers here represents a factor, right? And this is 1 factor with 3 levels, 1 factor with 2 levels, 1 factor with 4 levels. Now, if we're testing it statistically, if we're doing a factorial ANOVA to test the stats here, then the number of statistical tests you would end up doing as part of that, or that your stats program would do for you, is 1 test for each factor on its own, that's the main effect question, and 1 test for each combo of 2 or more of the factors, which is the interaction effect questions. Notice that the number of levels doesn't matter here. It doesn't matter what these numbers are when you're figuring out how many stats tests need to be done. It doesn't matter if it's a 2 by 2 or a 2 by 10. That's the same as if there's a 4 by 3 or a 4 by 87. All of those have 2 factors, so all of them would check for 2 main effects and then the 1 interaction effect. So all of those would just need 3 statistical tests. Now if you have 3 factors, as we saw in the slide before this, it'll always be 7 statistical tests. And actually by the time you get to 4 factors or more, it gets pretty crazy. So like with 4 factors, there are 4 main effects you would test, plus something like 11 interaction effects that you would need to test statistically. But regardless, for every single statistical test that's buried in this big factorial ANOVA that you're running, your stats program is going to give you an F value, which then you can, as always with an ANOVA, you can compare to an F value cutoff in a table using the usual degrees of freedom, or you can just check the p-value directly that your stats program gives you for each one of those tests to see if you should reject the null hypothesis, to see if it's statistically significant. So here's what the ANOVA table would look like for a factorial ANOVA with two factors. So just a simple factorial design that had two factors. It's going to be the same kind of thing we saw when looking into how a normal one-way ANOVA calculates the F value for it. F is always just variance of something divided by the normal variance in that variable. So mean squared deviation of something divided by mean squared deviation that's found in that thing itself normally, sometimes called the mean squared error. So mean squared of your factor A over mean squared error gives you the F value for your main effect test of factor A. So that's where you're getting the F value for, again, testing factor A statistically. You'll get an F value, mean squares of factor A over mean squares error. And then in light orange below that, I highlighted the next line. That's our test for the main effect of factor B. We need to eventually calculate through these intermediate numbers here. We're going to calculate the mean squared deviation for B. So that's just the variance within B. So MSB over the mean squared error. Just as we did before with the one-way ANOVA, that is just coming from the sum of squares divided by degrees of freedom. So basically it's an average. It's an average deviation. Like sum of squares over df is adding up and dividing by that number. So it's an average or a mean. That's where mean squares comes from. SS over df, that's what gives you the ms. And for each line, we're going to do it just, it's ms divided by the ms error, which is our overall variation in that variable. So in the darker orange here, we've got the output for how we would see an F value for the interaction of factor A and factor B together. Again, you would take the mean squares of A times B, or A and B together, but you divide that by the mean squared error to get the F value. In all cases, though, you're comparing the F value that you get, right? Whatever pops out here, whatever F value you calculate, you'll compare that to an F table to see if it's past the critical region cutoff and thus whether you reject the null hypothesis. Or as always, once you get that F value, you can translate it to a P value, and as always, you can just see if the P value is below 0.05. So that's what tells you if this test, if this line on the ANOVA chart here, if just this one test is statistically significant. So basically, for this table, this is what a stats program might pop out if you ran a factorial ANOVA on some study that had two factors. It would pop all this out, but for this table, there would be three p-values, right? They'd usually be right here next to the f values. There would be three p-values telling you if the main effects were significant and if the interaction effect was statistically significant. Now, as always, if the interaction is significant, then you definitely need to be careful about your interpretation of the main effects.